Hello once again, class, and welcome to another mock lecture. Today we're going to be talking about end behavior, relationships between number of turning points and x-intercepts, and overall what polynomials do as x values get really, really big or get really, really small. So there's a lot of different types of polynomials that exist with different numbers of turning points, different numbers of x-intercepts. But if we ignore all these turning point and x-intercept areas and only look at what's happening towards the ends of any polynomial, there's actually not that much variation in what polynomials will do. So this area in the middle that I literally call middle behavior, polynomials get their characteristics, right? They get all the different ways that they can look inside of there, but it's after this happens where polynomials start to kind of all behave the same. And what we're talking about are the areas that we call the left end behavior and the right end behavior of polynomial functions. Mathematically speaking, we're talking about where x approaches negative infinity, and this little symbol here, the arrow, means approaches, because literally x values are getting smaller and smaller and smaller, right? Where x is approaching negative infinity. And on the right, we're saying x is approaching positive infinity, right? Because that's where the ends of a polynomial are. Okay, polynomials can do one of four things. Both left and right can face up. Left can face up and right can face down. Both left and right can face down, or left can face down and right can face up. And that is it. That's the only thing that polynomials can do at their ends. They're not going to ever be flat or anything like that, because that's just not what polynomials do. And this end behavior is controlled really by two parts of the leading term of the polynomial. Leading term being this thing. Right? I wrote down the standard definition of a polynomial. The only thing that matters for end behavior is this stuff. None of this other stuff plays any role in what a polynomial ultimately will do. And the reason that is actually pretty straightforward. This is the highest degree term, so it has the most influence on what happens to x. So as x approaches infinity, when you raise it to the 7th power, let's say, that is so much larger than if you just raise it to the 6th that this just overpowers the entire rest of the polynomial function itself. So that's why we only have to look at the leading term here. But the first thing that controls it is the leading coefficient, which is your a sub n term. If that's positive or negative, that helps determine what's going to happen overall to the polynomial. And then the second thing is going to be the degree. If the degree is odd or even, that will also influence, what's going on towards the ends. And so the way that I think about this is I break this thing up in my head into kind of four different cases. It's two cases subdivided into two cases, basically. You have the case where n is even, and you have the case where n is odd. And then you have those subcases where a sub n, your leading coefficient, is positive, greater than 0, or a sub n, your leading coefficient, is less than 0. Those are the four things, right, that determine end behavior, and that's why there's only four possibilities. The first is that if n is even and a sub n is greater than 0, both sides are going to face up. The purple area in the middle, again, polynomials can do all sorts of different things, but, like 16x to the 4th will behave the same way as 16x to the 8th will behave the same way as like 7x to the 24th, right? All of those are even powers and all have positive leading coefficients. If n is even and the leading coefficient is negative, well, then it just faces down. Okay, so all that did was flip it upside down, like reversed the direction for each end, as it were. If n is odd, you have asymmetric end behavior. So left and right sides are doing different stuff. If your leading coefficient is positive, then your graph is falling on the left and rising on the right. And again, if your leading coefficient is negative, that behavior just gets reversed. So you can visually tell whether you're looking at something that has an odd degree, like x to the 2nd, x to the 4th, x to the 112th, or if it's asymmetric end behavior, then you're looking at some odd degree polynomial, like x to the 3rd, x to the 17th, x to the 101st, so on and so forth. So if we go back to our example where I kind of blotched all this middle behavior out, we can just very quickly tell which of these are even degree polynomials and which are odd. If there's asymmetry that's involved in the end behavior, then we know that it's odd. But all the ones where you have both sides agreeing, both sides doing the same thing, which are these three here, we know those are even, and the rest of them are going to be odd. Okay, so we get this. Furthermore, we can even tell whether their leading coefficient is negative or positive. The way that I look at it is if the right side is rising, your leading coefficient is positive. Because if you go back to here, the only time the right side is rising is when your leading coefficient is positive. right? The only time where the right side is falling is when your leading coefficient is negative. So the graphs where the function is falling on the right, those are negative leading coefficients. And the graphs for where the right side is rising, well, then those are going to be positive leading coefficients. But there's other stuff that we can examine as well. And here what I did actually is I put on the degree of the polynomial. So I graphed all these things on Desmos, so I know what the leading degree is. So I wrote them all here. But what I wanted to do was count the number of turning points first. So I recorded that. This polynomial had degree 3 and 2 turning points. This one has degree 1 and it doesn't turn at all. Right? This one has degree 6 and has 5 turning points. This one's 7 and 6. This one's 6, then 5. This one's 10, then 9. So there's a very telling pattern here. Okay, we'll list it in a second. Because the second thing I wanted to do was I wanted to look at x-intercepts. Now this one's a little bit trickier. This one is degree 3 and has 3. This one's degree 1 and has 1. But this one has 1 less x-intercept. This one also has 1 less x-intercept. 1 less than its degree, I should say. This one's 1 less as well. This one's also 1 less. But this still illustrates kind of the relationship between the degree and the number of x-intercepts. And here is that relationship. Let f be a polynomial function with leading coefficient a sub n and degree n. Then f has at most n minus 1 turning points. There was never a case where we had the same or more turning points than the degree. In fact, in our case, it was always exactly 1 less, which is not always going to happen. Sometimes you won't have that. Sometimes you'll have like 3 less turning points than the degree, but that's fine. Sometimes you have 10 less, but at most there can only be n minus 1 of them. And then for x-intercepts, it's actually at most whatever the degree is. And the ones that exemplified that were these two here, right? They both had the same number of x-intercepts as the degree, but all these ones had 1 less. That's why we're saying at most n x-intercepts. Okay, but then also n behavior, even though we broke it up into those 4 cases, we should go through the stipulated definitions of them. Again, you break them up into 2 cases. We'll start with odd. So suppose n is odd. The first case, the first subcase for this is when your leading coefficient is positive, and that implies that the graph rises to the right and falls to the left. Right, and that's how we would verbally describe this, what's happening here, right? Again, don't care about the middle behavior, it's what's happening at the ends. But mathematically speaking, there is a way to write that using this limit approaching notation. We translate rises to be y approaches infinity, right? Or f of x, which is a y value, approaches infinity, to the right, which translates as x approaching infinity, right? Because that's this way. So y is doing this as x is doing this, right? And that translates to this kind of diagonal movement. Falling is when y or f of x is approaching negative infinity, and to the left is x approaches negative infinity. If your leading coefficient is negative, that is flipped. So a sub n less than 0 implies f falls to the right, right? That's the difference. It was rising here. Now it's falling to the right and rises to the left, right? So opposite. So again, mathematically, f of x approaches negative infinity as x approaches positive infinity, and f of x approaches positive infinity as x approaches negative infinity. Falling to the right, that's what this says. Rising to the left, that's what this says. Okay, the cases where it's even are basically the same, except it's actually less to right because it's doing the same thing in both directions. So I said, suppose n is even. If you have a positive leading coefficient, that implies that f is rising to both left and right. And mathematically, the limit notation is a little bit easier. We say f of x approaches infinity, rises, as x approaches both positive and negative infinity, and that's to the left and right. Okay, and then if it's negative leading coefficient, then it's falling to both directions. F of x approaches negative infinity as x approaches positive or negative infinity. Okay, so that's all the information. Let's use this on some examples. All right, example number 1. Determine if the degree is odd or even, then determine if your leading coefficient is positive or negative. Okay, here's the function. Well, immediately I notice that it's rising to the right. So for me, first thing I assess is this has to be a positive leading coefficient. That is the only way you could have something rising on the right, is if it's a positive leading coefficient. Next thing I look at is that there's asymmetric end behavior, right? One side is going up, the other side is going down. The only place that happens is when n is odd. Okay, so it has a positive leading coefficient and an odd degree. Try this one. Go ahead and pause it here. Give this one a shot. All right, let's take a look. I got that n is even. and that the leading coefficient is negative, right? It's falling into really, again, for me, I only look at what's happening on the right. It's falling on the right, therefore it's got to be a negative leading coefficient. But then also both sides are doing the same thing. So it has, in that regard, symmetric end behavior. The only time that happens is when your function is an even degreed polynomial. Example number 3, determine the end behavior of this thing, right? This monstrosity. But remember, all of this stuff doesn't play a role. We just have to look at this, the leading coefficient's negative, and this, the degree's odd. So you just have to think about the definition. Which case does this happen, right? You can just even go to, okay, it's odd, and then it has a leading coefficient that's positive, that's negative, excuse me. So we must be there, and so we just record that. M of x is approaching negative infinity as x approaches infinity, which is falling to the right. And then m of x approaches positive infinity as x approaches negative infinity, which is rising to the left. All right, example number 4, determine the minimum degree of the following. Now, what we have to do here for minimum degree is first count up the turning points. Because remember, the number of turning points is equal to the minimum degree minus 1. The number of turning points is always 1 less than whatever the degree of the polynomial is. But anyway, here I counted 10 turning points. So if I want to solve for the minimum degree, we'd have to add 1 to that equation, plug in 10 for the number of turning points, and so 11 must be the minimum degree. All right, for example number 5, it says draw a polynomial with 6 turning points and 2 x-intercepts that also has a negative leading coefficient. The way I'm going to start this is with the x-intercepts. Let's just plot those things. It doesn't specify where they're supposed to be, so let's just put them anywhere. Now, because it says it has a negative leading coefficient, I know this thing's falling to the right. Okay, we don't at this point know if it should be rising to the left or falling to the left because we don't know if the degree is going to be even or odd. Future mock here, we actually do know if it's going to be even or odd degree because an even degree polynomial function can only ever have an odd number of turning points. That's what would make the end behavior the same in both directions. But I'll just continue on with the video. So what I do is I just try stuff. Okay, so maybe what I'll do is I'll have it intersect here. So there's one intersection, and then it can't intersect until down here again. So let's put all the turning points above the x-axis. So there's 1, 2, 3, 4, and then 5. And if I were to have it come down here and cross again, I'm 1 turning point short, right? It needs to turn again. Yeah, see, this is what I was talking about. A odd degree polynomial has to have an even number of turning points, and so since this one has 6 turning points, we know it's odd degree, so we know that it should be rising to the left. Similarly, even degree functions have to have an odd number of turning points, like I said before. But the interesting thing is that if I have it turn earlier, like this, well, now I've got 6 turning points, but then it doesn't reach this x-intercept. So that can't be it. But we do know that it should be at this point rising in this direction. All we need to do is maybe move this down to be coincident with that x-intercept here. But we know the end behavior needs to be like this. So what I had before I think is a reasonable attempt at this. So there's 1, 2, 3, 4, 5, and then we'll come down here like this, 6. That looks terrible, but you get the idea. I actually did this. I don't remember what I went with. Oh, I went this way. Okay, so I put the rebounding here. But yeah, this also works. So all my turning points are below the x-axis, although one of them is on it. So I got 1, 2, 3, 4, 5, and then 6 is right here, and then it intersects the x-axis. So there you go. There's actually 2 different ways that you could draw this thing. I think I locked that one in, yeah. Example number 6. If possible, draw a polynomial function with 4 turning points that is even. Okay, now notice it doesn't say even degree, it says even, which means we're talking about it's got to be symmetric over the y-axis. Now, you could answer this actually without drawing it at all. And the way that I would do that is by noticing you need to have 4 turning points, which means the minimum degree that this polynomial is actually 5, which means it would have asymmetric end behavior, right? That can't happen. If you want to draw it, we could try. I want it to continue, first of all, I put 3 turning points on here. It needs a 4th, but for it to be symmetric, it would have to do this, right? It'd have to keep going down, but then I lose my 4 turning points. I don't get that fourth one. It would have to do something like this, which means that it's not reflective over the y-axis, and so therefore it can't be done. I also can't bring this up, because then even though it's symmetric now it's got 5 turning points. Okay, so this one's not an even function, and therefore is not possible. All right, number 7, the last one. If possible, draw a polynomial, probably that should say with, hopefully that's in there in the next slide, 1 x-intercept and turning points at these 4 points here. Okay, so the first thing that I did is I plotted those points. -2, -6, 0, -2, 1, -5, and 2, -3. And remember, these are all the turning points of the graph. So based on the way that they are, I kind of already know what type of turning point it is. And what I mean by that is, like, we know, for example, this one is not going to be this type of turning point, because then how would it hit these other ones down here? Instead, it has to be something like this, right? And then this one has to be something like this. And then this one has to be something like this. And then this one has to be something like this. So like we know some parts of the graph here. And so I went ahead and filled that in first. Now it says there's only supposed to be 1 x-intercept, and we know there's no other turning points. So I think the only logical way that we could continue this is to have the left side just continue up and intersect the x-axis, and the right side just continue down. And there you go. We're done. Okay, so there was quite a few examples over the different types of questions that you're going to face for end behavior and minimum degree stuff. But hopefully you guys learned something. If you have any questions, just leave a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.